Okay, as we were discussing in the last video, so we can implement any given Boolean expression using the ratioed logic. The advantage of going for ratioed logic is if the number of inputs for a particular gate is equal to n, supposing that you want to implement a 10 input NOR gate, NAND gate or whatever, the number of gates that were required in case of static CMOS implementation was 2 times n. But in case of this pseudo NMOS implementation, the number of transistors required are simply n plus 1. As the value of n is keep on increasing, then this 2n will be too large, whereas in case of pseudo NMOS implementation, the number of transistors that will be saved in implementation will be huge in number. Suppose if n is equal to 20, so here you may require 40 gates, here you may just require 21 gates. The only limitation in case of pseudo NMOS transistor is the output is a ratioed logic, meaning the output not only depends on the dimension of the transistor, it also depends on the dimension of this. To overcome this, we have to ensure that the resistance offered by this should be sufficiently more compared to the pull down resistor, so that this is not always making this go high. Suppose if you make it too high, of course it may take some time to just make it to logic 1 whenever these two are off. If the resistance offered by this is more, then it may take slightly more time to go to VDD. So the output may take some time to go to VDD. Of course, this is the major limitation of this pseudo NMOS implementation. So let us see one more logic where we have a slightly different thing compared. Of course, along with that problem of pseudo ratioed logic, in case of pseudo NMOS, what we have is there is a possibility of static depot dissipation. If you can see here, for any given combination of 4 possible combinations, one of the transistor will be always off. That is, there is no rail-to-rail connection from VDD to ground in the static CMOS implementation, whereas in case of pseudo NMOS, there is a possibility of static power dissipation, because when A and B is equal to 1 1, since this pull-up transistor is always on, so there is a possibility of static current flowing from VDD to ground. So this will certainly increase the static power dissipation of this pseudo NMOS transistor. The two major limitations of this pseudo NMOS is it is a ratioed logic output, and there is a possibility of static power dissipation. And the major advantage is number of gates required to implement a Boolean expression be n plus 1. So let us see, is it possible to improvise the advantage of the pseudo NMOS. So there is a logic called as dynamic Cmos. So this is dynamic Cmos implementation. In this dynamic Cmos implementation, so let us again take the same NAND gate. So here what we're going to have is, we will going to have again the same pull down network as we had it in case of pseudo NMOS, as well as the static CMOS implementation. Now along with that, we're going to have this is having two extra. This is VDD, this is VSS. This is driven by a clock. So there is an extra input that is there. This is not for this is not like conventional sequential logic. This is still a combination logic. This is y is equal to a and b. So this dynamic CMOS has got two phases of implementation, that is operation. The first phase, it is called as pre-charge. So when I say pre-charge, so V0, that is V out, which is nothing but this output, will be made equal to VDD. So pre-charge means the output is made always equal to VDD, irrespective of the Boolean expression you are trying to implement. Whatever the Boolean expression you are trying to implement, of course in this particular case we are implementing a NAND gate. Whether you implement NAND gate, NOR gate, AND gate, whatever, One second.
ನಮ್ದು ಅದೇ ನಾವು ಆನ್ಲೈನ್ ಮಾಡ್ತಿದೀವಲ್ಲ, ಸೊ ಅದೊಂದು ತಗೊಂತಾ ಇದೀನಿ. ಒಂದು 2-3 ಜನ ಮಾತ್ರ ತಗೊಂತಾರಂತೆ. ಅಂದ್ರೆ ಈಗ ನಾವು ಆನ್ಲೈನ್ ಮಾಡ್ತಿದೀವಲ್ಲ, ವಿ ಆರ್ ಟ್ರೀಟಿಂಗ್ ದ್ಯಾಟ್ ಇಟ್ ಸೆಲ್ಫ್ ಲೈಕ್ ಓಕೆ ಆಫ್ಲೈನ್ ಇದರ ತರ. ಅವ್ರು ಇಲ್ಲಿಗೆ ಬಂದ್ರು ದೇ ಮೇ ಡಿಡ್ ನಾಟ್ ಹ್ಯಾವ್ ಟು ರಿಪೀಟ್ ದ ಸೇಮ್ ಥಿಂಗ್. ಹಾಗಾಗಿ ನಮ್ದು ಆಲ್ಮೋಸ್ಟ್ ಎಲ್ಲ ಲ್ಯಾಬ್ಗಳದು ಅವ್ರು ಬಂದ್ಬಿಟ್ಟು ಇಲ್ಲಿ ಒಂದು ರೆಕಾರ್ಡ್ ತರ ತೋರಿಸಿ ಮಾಡೋದು ಅಂತ ಇದೀವಿ. ಹೌದೌದು ಹೌದು ಹೌದು ಅಷ್ಟೇ. ಹೌದೌದು. ಕೆಲವರು ದೋಸ್ ಆರ್ ನಾಟ್ ಹ್ಯಾವಿಂಗ್ ದಿಸ್ ಇಂಟರ್ನೆಟ್ ಇಶ್ಯೂಸ್, ಅಂಥವ್ರಿಗೆ ವಿ ಆರ್ ಮೇಕಿಂಗ್ ದಟ್ ಇಲ್ಲಿ ಬಂದು ಮಾಡಬೇಕು ಅಂತ ಹೇಳ್ತಾರೆ. ಅದೊಂದು ಸರ್ವೆ ಮಾಡಿಸ್ತಾ ಇದ್ದೀವಿ. ಒಂದೊಂದು ಲ್ಯಾಬಲ್ಲಿ ಒಂದು 4-5 ಜನ ಅವರೇ. ಅವ್ರಿಗೆ ಇಂಟರ್ನೆಟ್ ಅಥವಾ ಲ್ಯಾಪ್ಟಾಪ್ ಇಲ್ಲದೆ ಇರೋರು, ಅವ್ರುಗಳ್ಗೆ ಏನಂದ್ರೆ ವಿ ಆರ್ ನಾಟ್ ಇಮಿಡಿಯೇಟ್ಲಿ ಕಾಲಿಂಗ್ ದೆಮ್, ಸ್ವಲ್ಪ ಟೈಮ್ ಕೊಡ್ತಾ ಇದ್ದೀವಿ. ಇದಕ್ಕೆ ನಾನು ಜಸ್ಟ್ ಅನ್ಸುತ್ತಂದ್ರೆ ಅದು ಅದು ಅದೇ ಅದೇ ಹೌದು 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 ಅದೇ ಹೌದು ಹೌದು ಹೌದು. ಓಕೆ, ಅವಾಗ ಒಂದ್ಸತಿ ಮಾತಾಡೋದು. ನಾನು 7th ಅವ್ರ ಹತ್ರ ಮಾತಾಡಿದೆ, 6th ಅವ್ರ ಹತ್ರ ಅದೇ ನೆಟ್ ಊಟ ತಗೊಂಡೆ. ಸರಿ.
Okay, sorry. During this pre-charge condition, irrespective of the combination that I want to implement, the output will be made equal to VDD. So this will happen as per this circuit diagram. This will happen when clock is made equal to 0. When clock is made equal to 0, this is called as pre-charge. What is pre-charge is output is made pre-charge. The output is made equal to VDD when clock is equal to 0. The second phase of the evaluation or second phase of the operation is evaluation. So this is evaluation phase. So this is the important or the phase in which depending on the Boolean expression what we have implemented, clock is made equal to 1. The output whatever we are expecting is purely as per our requirement. Now output is no more VDD. Output will be equal to the expected logic, which is A and B. Of course this is the NAND of the implementation. That is called as evaluation. So we have two phases here. So one is called as pre-charge period where clock is 0, and the other one is the clock 1 where we are making this off, this is on. Then depending on the combination of A and B, I will get the corresponding output. See now, only difference is at any point of time, whether you are there in the pre-charge condition or evaluation condition, one of the pre-charge transistor or the evaluation transistor, if I call it as MP and this is ME. ME is the evaluation transistor, MP is the pre-charge transistor. During pre-charge this is on, this is off. During evaluation this transistor NMOS is on, PMOS is off. So one of the major limitation of this pseudo NMOS where there was a static power dissipation has been totally avoided. There is no path from VDD to ground at any point of time because either of these two phases of pre-charge or the evaluation, one of the transistors is off, and we have the output y is equal to A and B. Again, in the previous case, what is this now? So now we have this A and B. So since it is this is on during the during the evaluation condition, depending on the AB value, the output will either become 0 or 1. So suppose in this case, if AB is 0, 0, then Y, since the Y was already pre-charged to VDD, it remains at VDD. It remains at VDD because there is no path. Even though this is on, since these two are off for this A and B combination of 0, 0, it remains at the pre-charge value of VDD. Because this was VDD, not because this is actually on during the pre-charge period. So actually what happened was, so this was made always high. So what we can just think of is, we can have this as my clock, this is clock. So clock is first made 0 and then made 1. This is 0 1. So now if you consider this as my AB, so irrespective of the value of AB here, so it can be XX, so it can be either 0 or 1, so it doesn't matter the output. Suppose if I say Y, during this 0 it is equal to high, so this is now high, so this is logic 1, because now you're in the pre-charge period. So once it goes high, assume that this is now 0, this is also 0, so we have a 0 0 combination. This is 1. Since it was pre-charged to 1, it remains in pre-charge condition, of 1. Suppose if you make this 1 and if continues to be 0, since even though this is 1, this is 0, because only A is 1, this is made 0. Since there is one transistor is off, it is not again having a path for discharging. This remains to be there in 1. Then suppose if you make this also 1, this is 1 1. If you make these two 1 1, the output will become 0. Now suppose if you make this one of them 0 and of course one of them as 0, other 1 1, this won't go high. Because this is always off. This is off during the evaluation period. So what is very important in case of dynamic CMOS is, if you want to find the combination, the output for a given combination, you have to always do a pre-charge and evaluation. So here you can see we have pre-charged this once, and I'm trying to do the evaluation of this and this simultaneously. Till this point it was fine, so I was getting the expected value. Of course till this point it was fine, but over here it is not coming. Suppose if you have started this as 1 1, and if you make this equal to 0 1, something like that, so it would have been valid for only this combination. The subsequent combination would have failed here. So that's why in case of dynamic CMOS verification, for every combination verification, first we need to do a pre-charge and then evaluation, give A and B, then check it out. So what I mean to say is, first you have a pre-charge evaluation. This is pre-charge evaluation. Give A as 0 0. This is A 0 0. Then you do one more pre-charge, one more evaluation. This is pre-charge evaluation. Make this as 1, make this as 0. Then you again pre-charge evaluation, make it as okay, we can make it as 1 1. Now you can see, now depending on the input, and the output will be either made 1. Of course during this pre-charge period, irrespective of whatever the output combination, sorry, the input combination, this is high here. Again you can see this is high here. Can you see this is high? And then over here this is still high, and this is high because it is 0 0 and you are getting an output of 1. It is now 0 1, the still output is 1. Now here this becomes 0, now you again do one more pre-charge, so pre-charge becomes, output will become high. And then depending on the next combination, the input voltage, output is decided. So in case of dynamic CMOS, before we actually find out what is the output, we have to always do this operation of pre-charge and then evaluation. So this is not allowed, because this may end up with erroneous results. So before, if you want to verify this particular combination, do a pre-charge evaluation for each and every combination. So this is the type of input pattern, that is pre-charge evaluation clock, that will be done before evaluating the result. Okay, let us see what are the signal integrity issues with this particular dynamic CMOS. Let us go one by one. So what are the different issues that we're going to end up with in analyzing or in using this dynamic CMOS logic. So one of the major issue in using this dynamic CMOS is let me just come to that. So let us consider a very simple logic, which is something like this. This is VDD. I have this as, just take A is equal to 1. This is clock bar. Okay, this is clock here, and this is also clock. Okay, let me consider this is clock and this is Y. This is Y here. Let me just make this equal to 0, then make it 1. So let us see what is, if it is 1, see now, okay, since clock is equal to 0, output is naturally high in the magnitude. Is this fine here? So is this high? This is logic high because this transistor is on, the output is at high condition. Assume that this is high for a longer time. Since it is high for a longer time, so we know that this is an NMOS transistor, the substrate is P. Can you just think of having a diode from this drain to source? Can you just think of having a diode which is of this type? So of course I'll just rewrite it. So this is my P substrate, and is this my, I'm just exaggerating this. Will you have a diode something like this from drain to the bulk? So there is a drain to the bulk. So because I know that drain is NMOS and the bulk is PMOS. See now, what are the voltage you are looking at? You are looking at a voltage of high. So this is usually grounded. The bulk of a NMOS transistor is grounded. Can you see now, this is high, this is low. So is it in reverse bias condition? This in reverse bias condition. Even though this is in reverse bias condition, assume that if you keep on making this high for a long time, what might can happen is there can be a leakage current. There can be leakage current from this output point to the ground point here through this reverse biased diode. So since it's a reverse bias diode, there is a possibility that there is a leakage current. Because of that leakage current, the output voltage was supposed to remain at VDD may start reducing. This is, I'm talking about if you leave it for a longer time. If you leave it for a longer time, the output voltage may drop down. Suppose assume that if it is there till this point, can you see it was supposed to remain at VDD, but by this time the output would have been reduced to very low value. So in such case, whenever you are implementing this type of dynamic logic, it is always necessary that this charge leakage, we call it as there is a charge that was there accumulated in the load capacitor, has been leaked to ground through this reverse biased diode. So to avoid this charge leakage, what they will do is they always pre-charge in regular intervals. So the clock will never be made 0 and then it will not be made 1 for a long time. So they'll be applying a clock which is something like pre-charge, evaluate, pre-charge, evaluate, pre-charge, evaluate. So this pre-charge will make sure that, assume that if I'm just continuing this, so can you see here, whenever it is pre-charge, this goes high. So this may slightly drop here, and because you are doing the pre-charge, it will again go high. Can you see this is keep happening? So this is a type of process that will be done for this particular dynamic logic implementation. So to avoid this charge leakage, what they will do is they will make the clock will be always made. Of course, you'll be keep on pre-charging the things at a regular interval. So this is one possibility of avoiding this charge leakage. The other possibility is you can just think of, for the same logic, for the same thing here, So let me just consider this is your clock. Again, this is your clock. This is for pre-charge, that is for evaluation. This is your A. What you can do is to avoid that charge leakage. I can have, okay, this is Pmos transistor. I can have one more transistor which is ground. See now what are the advantage here. There was a possibility of output voltage that is stored here. The charges that are stored in this output capacitor was being get leaked here. When it was get leaked, you are supposed to pre-charge all the time using this transistor. But if you can see here, suppose, of course, this leakage will comes into picture only when the output voltage is high. If the output voltage is high, since you are you are in the evaluation mode, so there is no path for this to get the charge. So you provide an extra path through this transistor to ensure that this is made equal to VDD. So whenever this voltage tries to drop down here, so this is again made equal to VDD because this is always on. This is always on. Since you are grounding this will never make the voltage over here to go down, because this is going to provide the required charge for this to be maintained at VDD. But you can see this will certainly have an issue. Suppose if you have the output voltage is 0. If the output voltage is 0, since you have this logic to overcome the charge leakage, since this is equal to what? This is equal to, this is always on, whatever charge you had it as 0 might be get filled by this transistor which is on. So you may not get it as 0. So why you're not getting it as 0 means because this is always made on. This is always made on. So this type of this type of transistors which are used to keep the voltage this at VDD when the output was VDD is good when the output voltage is supposed to be VDD. But it is so bad if your output, assume that this is equal to 1. When this is equal to 1 during evaluation period, you are supposed to get a 0. Since this is on permanently, you will end up with an issue here. You'll end up with an issue. This may not become 0. This will be again being always charged. You'll end up with a ratio problem here. To overcome that, instead of grounding this all the time, so you turn on this only when the output is high here. When the output is high, then only you make it. So what I'll do is, there is a slightly modified circuit here. So this is clock for pre-charge, this is a clock for evaluation, this is A input. I'm going to use a bleeding transistor. So bleeding transistor, why the name bleeding transistor given is, whatever the charge that is lost due to charge leakage will be compensated by this bleeding transistor. So this is now VDD. Now you can see we are using. So when does this transistor will be on? This will be on only when the output is high. So instead of making this on for all the time, so I am making this on only when the output is high. If the output is high, this was supposed to remain at VDD. Whenever a charge leakage happens, this one will make it as 0. When this is 0, this is turned on so that you can retain this at VDD. You can retain this at VDD. Suppose if this is at 0 volt, if it's at 0 volt, of course it is supposed to remain at 0 volt. There is no question of leakage. But in the previous case, when it was 0, since this was turned on permanently, you keep on getting the charge. So that issue is not here. When this is 0, this is 1, this is off. There is no question of charge being filled into this. So this is a slight modification or slight improvement in case of implementation of a bleeding static transistor to overcome the charge leakage. So we will see two more issues with this dynamic or few more issues with this dynamic logic in the next video.